All right, well, we're going to be working with continuously compounded interest. This is interest that's not compounded annually, monthly, quarterly, daily, but continuously, every moment, every second. And we have a formula or an equation for that. We've used something similar to this in other examples where we've looked at exponential growth or exponential decay. But specifically, when we're dealing with continuously compounded interest, within our equation, we have the natural base E. So here's our formula. We got A, that's our account balance, let's say, or final amount, equals P, our principal, and then that is times the natural base E raised to the power of RT, where R is our rate of return in decimals, and T is our time. And in the examples we'll be working with here, that T is in years. That's our unit of time, is years. And we're going to be taking that formula, and in one case we're going to find for A, the final amount. Another one we're going to be trying to find P, the original principal we need. And a third time we're going to solve for R, a projected rate of return. Well, let's get started on this. Let's see. If Angela's grandparents invest $8,000 at 3.75% interest compounded continuously, how much money would be in the account in 30 years? Well, we're trying to find A in this case. How much money would we have after investing $8,000 at 3.75% with interest compounded continuously after 30 years? And so let's just plug and chug our way through this. So we got A equals $8,000 times E raised to the power of 0.0375. That's our rate of return expressed in decimals times 30. And when I solve all that, it's $24,641.73. So after 30 years, at a 3.75% return compounded continuously, $8,000 will be worth have grown to $24,641.73. All right, well, we're trying to make some decisions on different things. Angela's grandparents are, so let's look at a different scenario. If they could only deposit $10,000 in the account, at what rate would the account need to grow for Angela to have $30,000 in 18 years? So obviously now they're thinking about a college fund. They're wanting to have $30,000 in 18 years. They got $10,000 to invest, and they're trying to say, well, what kind of rate of return do we need to achieve our goal to have $30,000 in 18 years? And again, we're just going to insert this information into our formula and solve for the missing variable. All right, well, we got $30,000. That's the amount they want to have, equals $10,000, the amount they start with, times natural base E, raised to the power of 18x. And the 18, of course, is the time in years. And X, I don't know why I didn't use R. Could have used R for rate of return. I don't know. I just like X sometimes. It's kind of my default variable. That's the rate we're trying to determine. What rate do we need to invest after investing $10,000 with an interest? What rate of return do we need that is compounded continuously to achieve our goal of having $30,000? Well, let's see. I could take the $30,000. I could divide both sides by 10,000. I'd have 30,000 divided by 10,000. Well, of course, that's 3, and that would leave me with E raised to the power of 18x. Now, we should know that I could take the natural log of both sides of this equation to kind of get rid of the E. And when we do, I've got ln of 3 equals ln of E raised to the power of 18x. X, the rate of return, is what we're trying to find. And the ln and the E cancel. That's just 1. And let's see, then that's going to leave me with ln of 3 equals 18x. We can divide both sides by 18 to isolate the x. And when I put that in my calculator, ln of 3 divided by 18, we're going to say that our rate of return needs to be about 6.1%. Oh, let's look at this one other way. All right, now if Angela's grandparents found an account that paid 5% compounded continuously and wanted her to have $30,000 after 18 years, how much would they need to deposit? All right, so our missing variable now is this P. How much do we need to invest initially? They've got an account of 5,000. They have a goal of having 30,000. They want to have that to be 30,000. Have grown to that after 18 years. Well, let's see. I could just take the $30,000 and divide it by E raised to the power of 0.05. That's my 5% interest compounded continuously times 18. And let's see, $30,000 divided by E to the 0.9. Now that's what I get when I take 0.05 and multiply it by 18. I just went ahead and did that step here. Got that from here. And $30,000 divided by E raised to the power of 0.9 would be 12,197.09. And that tells us how much money Angela's grandparents would need to invest in a 5% account that was compounding continuously, the earnings being compounded continuously, to achieve $30,000 in 18 years, 12,197.09. Pretty neat, huh? Angela's got some nice grandparents.